All right, so let's go ahead and get started again. Oops, one more time. All right, so let's go ahead and get started again. So what we have left in the chapter is about 45 minutes worth, and I think that's probably too much to do tonight. So what I decided is for your exam material, it's going to end here. So I'm going to put a note here, end of exam 2 material. So the material that's below this line, this will be for exam 3. So I'm going to put a note here that says exam 3 material. I trust you guys won't be too heartbroken that we're going to break for the exam right here. All right. I think that the exam's going to have enough tough concepts on there with the Hess's law and the other things without adding bomb calorimetry and heating cooling curves, which take quite a bit of both time and effort to kind of go over and learn those. So again, we're going to end the exam material here. So exam 2 material is above the line, whereas exam 3 material will be below the line here. Okay, so any questions about that? All right, so I want to go over the lab with you, but just as a reminder, the exam is scheduled for Wednesday, 2 weeks from today, because next week is spring break, but I am around, so if you want to email me, we could set up a Zoom session if you want to go over some stuff, or if you just want to email me with a question, we can do that as well. So I haven't converted the exam to online format yet, but my hope is that it'll be similar, where it will have multiple choice, free response, and then some for you to calculate out. And I'm not entirely sure how I'm going to work that out. I might have to have you write it on a piece of paper and take a picture of it. So still working out all those details. I'm going to give you guys 3 hours, but I'm writing it to be about an hour and a half. So that should give you plenty of extra time in case you need that extra time. But any questions about that exam, about the material on the exam, or anything else? All right, so let's go ahead and start talking about your lab. All right, so a couple things about the lab. First off, this is lab 5, and the class data that you're seeing right here, this is already on Canvas, so it's in the lab notes section. And just like last time, I'm going to ask that you write this into your own data sheet. If you don't have a data sheet, you can write it onto a piece of paper. Make sure you use pen. And the pen you only need for this data right here. Any of the calculations could be done in pencil. So any questions about that, about where you're going to get the class data? All right, so next up, I want to go through the lab a little bit with you. But first of all, on our YouTube channel, Dr. DA did a great job of going through the experiment and narrating the experiment. So I'm going to strongly encourage you to watch his video. So he does an introductory video, and then he does about 30 minutes where he walks you through the entire experiment. So I'm going to, again, ask you to do that rather than walking you through the experiment. But what I want to do is walk you through calculations and the post-lab questions. So he does have a calculations video, which I think is a great video. But I'm just going to go ahead and walk you through this just so you can see what I did in these lab notes here, which I'm going to be posting. And here we go. Okay. So let's go ahead and go over this. Oh, by the way, do you guys need any time to get out your Lab 5 notes for Lab 5? Yes, no? Can everybody hear me okay? Everybody's been super silent. So no meaning you can't hear me, or no meaning you don't need time to get out your lab notes? Yes, you can hear me. Okay, perfect, perfect. Everybody was really quiet, so I wasn't entirely sure. Okay, so what I've done, and again, these will all be posted up. So I have labeled A, B, and C, your first 3 measurements here. So A is mass of test tube plus beaker, and B is mass of test tube, sample, and beaker, but it will have compound in it. And then C is mass of test tube plus product and beaker. So essentially A is empty, B has the original compound, and then C has your final product after heating. And then down here we have number 1, which is your mass of sample, 2, mass of oxygen, 3, mass of KClO3, and then 4 is your percent of potassium chlorate. So let's take a look at number 1. So number 1 is the mass of your sample. You're going to take the mass of essentially the empty setup, which is the test tube. You're going to take first the sample, the test tube, beaker plus sample, which is labeled as B, and you're going to be subtracting out the test tube and the empty beaker. So essentially you're trying to find out how much solid was put into your test tube by subtracting the weight of the test tube with the sample minus the test tube empty. So that's what you'll be putting into number 1, and again it's going to end up being B minus A here. So any questions on number 1? All right, so number 2 is the mass of oxygen. So in this experiment, what you did is you heated a test tube and you drove off oxygen gas. So the difference between your original sample and your final product is the oxygen that has essentially left. So you lost oxygen and only oxygen. So what you're going to be doing in 2 is to find the mass of oxygen, look at the difference in the masses or the difference in the weights. So you're going to take the mass of the original sample and subtract out the mass of the final product. So here is B and C, and notice both of them come with the mass of the test tube and the beaker because you would be weighing it in a test tube and beaker. Any questions about that mass of oxygen, how you're going to be essentially taking the mass of the sample and subtracting out the mass of the final product? All right. So next up is the mass of potassium chlorate. So when we give this to you, we give you a mixture, and only one of the components is potassium chlorate. So you can't just say that, hey, this is how much it weighed, and so I can use stoichiometry to find potassium chlorate. What you're actually going to be doing is starting with your grams of oxygen that you found right up here into mass of oxygen. And now you'll use stoichiometry, going from grams to moles, and then you'll do a mole to mole conversion between oxygen and KClO3, and finally you're going to go from moles into grams. In order to do this, you need a balanced chemical equation. I've given you a chemical equation, but it is not balanced, so I need you to balance this. So I'm going to put a note, balance first. All right, so any questions on how you're going to do that stoichiometry in number 3, where you're going from the grams of oxygen that you found above into grams of KClO3? It's your standard gram to gram conversion, but you need to balance that equation that I gave you. All right. Next up, you need to find your percent of KClO3. So if this was a regular semester, I would be giving you guys unknowns. In this case, I'm just giving everybody the same data set, but you would be finding the percent of KClO3 in your unknown. So you're going to take the grams of KClO3 that you found above here. So you would get an answer, and the answer to number 3 here would be your grams of KClO3. And then you're going to divide it by the grams of your sample, which is from number 1. So number 1, way up here, is this right here. So what we want to do is determine how much KClO3 was in your original sample. So again, you're taking 3, your answer to 3, divided by your answer to 1, and then multiplying it by 100 to get into percent. There we go. All right, questions on anything about how you're doing 4 here? All right, so this is going into where you see 1, 2, 3, and 4 on your results table. Remember, all of this can be in pencil. The only thing I need in pen is the actual measurements, which you are copying off of the sample data. All right. So next up, average KClO3. So you're given data for 2 trials, and you need to average those together. Same way you would average anything, add them together, divide by 2. And so that goes into this box right here. All right, mass of oxygen. Now this is something that trips people up, and the reason is you've already calculated it right here. So you're just transferring it over. And that seems really weird. Like, why do we have a spot for the same thing? Why do we have 2 spots for the same thing? And the reason is you're going to need that for the calculation below. And whoever created the table just thought it would be nice to have it more convenient so your eyes didn't have to look all the way up like 2 whole inches. I don't know. All right, so just again to warn you, you're writing the same value in 2 spots. All right, so next up, you are going to convert grams of O2 into moles of O2. So that is just using your molar mass. And thank you, Tasso, again for laughing at my bad jokes. All right, so moles of oxygen, again, grams to moles, just using your molar mass. And then next up is the volume of oxygen in liters per mole. So here, these are your liters, or for us, it is our liters, because we all have the same data, divided by moles of O2. So the moles you've just calculated, this goes right down here. Now we need to know your volume in liters, which I have highlighted in brown here. And that's it right here. So your very last data point here, volume of water in milliliters, you need to convert that into liters. And that's the top part here that's in brown. And then you divide by the moles of O2 that you found right here where it says moles of O2. Okay, questions about anything that I've gone over so far here, average percent, mass of oxygen, moles of oxygen, or volume of oxygen in liters per mole? All right, so next up, we're going to talk about the pressure of water. So here, this is a table on page 14, and I have copied it into here just in case you don't have your lab packet. And here it is. Let's see. All right, so let's skim down to this one right here. There is our table. All right, so we need to know the pressure of water at your temperature. So you're going to look up the temperature that you have for your data. All right, so you need to look at your temperature here, and then you're going to find the pressure of water at that temperature. So let's just imagine, actually, we don't have to imagine. Let me pull up your sample data. All right, here it is right here. So we have 23.0 degrees Celsius. Right over here. Here is your vapor pressure, and it is 21.1. It's already in TOR. Just go ahead and report this value. So I've already found your trial 1 value for you. For trial 2, again, you'll just look up your temperature and report the vapor pressure that's given here. So again, if you don't have your lab notebook, it is here in our lab notes. So any questions about how to find the vapor pressure for the water? All right. All right, so again, it's already in TOR. You don't have to worry about it. Oops, I highlighted the wrong temperature there. All right, so the temperature you'll be looking at is the one up here. All right. Okay, next up is PO2 dry. So we talked about once upon a time that whenever you collect gas over water, you need to subtract out the water vapor, and that's what you're doing here. So to find your PO2 dry, you're going to take the total barometer pressure, and that's data that's given to you right up here. And then you're going to subtract out the water from this right here. So total pressure minus the water pressure will give you your pressure of oxygen, and that is the true pressure of oxygen, which here we're calling PO2 dry. So this is the same as what we did in class when we collected collected gas over water. We did that example in class. But any questions about this? All right, so next up is temperature. You'll take the temperature that's given in the data set and add 273.15 to put it into Kelvin. And then I'm going to go over the volume of oxygen because it's a little more detailed with you. But any questions on anything that we've talked about so far? Tasso, I like how in your chat it just says no, 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 because you're the only one who answers when I ask if there's any more questions. All right. All right, so let's talk about number 6. So number 6 is a little bit more tricky. And notice I have labeled this calculation right up here as number 5. We're going to need this in our calculation for 6. All right, so here was 5. Remember, volume of O2 in liters per mole. You put your volume in liters, or in this case, our sample data. You have to convert it from milliliters to liters. Then you will divide by moles of oxygen. Now here is 6. So if you remember way back to last class, we talked about our favorite equation, PV over NT equals PV over NT. And in this case, we have the same number of moles, so we have crossed out the moles, and we end up with our combined gas law, which is PV over T equals PV over T. Now here, in number 5, you calculated what I called V for the lab. So that is the volume for the lab in liters per mole. You know your pressure of oxygen because you calculated that out when you withdrew the pressure of water. And by withdrew, I mean subtract. So you took total pressure minus pressure of water. That gave you your pressure of oxygen. So that's already calculated in your table. And then T for the lab, that's your temperature from the lab in Kelvin, which you've also already calculated. So everything here on this left-hand side, you've already calculated it. It's already in your table. Now on the right-hand side, you have P at STP. So what we know about STP is it's 1 atm. However, we have this pressure right here in torr. So what is the pressure at STP in torr? If it's 1 atm, what is that in torr? Anybody remember way back? There we go, 760, excellent. So there's a note right here that says make sure your units of pressure match. So very common mistake I have on here is people will write 1 right over here for 1 atm, but they'll put the pressure over here in torr. So make sure those match. My recommendation, just use torr for both of them. Thank you everybody for putting in the conversion for atm and torr. All right, so volume is what we'll be solving for. And you all know your temperature at STP. So temperature at STP is going to be 0 Celsius or 273.15 in Kelvin. All right, so you will solve for that V that's got the purple box, it's kind of an orangish color and it's got the purple box around it. This one right here, that's the one you're going to solve for. And it's going to be your experimental value at STP. So what we're taking is your volume, but we're adjusting it to STP because what we want to do is compare your experimental value to the true molar volume, which is 22.4. So this is a way for us to check and see how good you did in your experiment, or in this semester, how well you did in your calculations. So because we know that this is good data, you should have a relatively small percent error. If you're coming up with like a 200% error, it has to be calculation based, and please send me an email, let me know so I can help you out. So once you get that value for V, that is number 6, and your percent error is going to be the absolute value of that value minus 22.4. Just in case you don't remember from way back when in math class, absolute value means just report it as a positive, divide it by 22.4, and then multiply by 100. So give me the positive percentage of how different your value is than the accepted value of 22.4 liters. All right, questions on how you're calculating out your percent error? All right, So that is way up here. So here I've labeled number 6. That was your calculated value of V, and number 7 is your percent error. Even though it gives you all these boxes, you will only have one, or no, I take that back. You'll have 2% errors, one for trial 1 and one for trial 2, because you're going to do those separately. All right. All right, so questions on anything with the lab calculations? All right, so if you were thinking, hey, it'd be really awesome if an instructor would walk me through a full set of data and show me how all of this works, that is what Dr. DA did in that video that's on our YouTube channel. So in case you're thinking that's not enough of an explanation, or it was a fabulous explanation, but I'd love to see somebody walk me through the data, that's what Dr. DA does. It's about a 30-minute video on calculations, and it's a wonderful video. He does have, I let him borrow my iPad, and it was his first time on the iPad, so you'll notice there was a few little problems he had, but he figured it out along the way. So it's still a great video. All right. Questions on anything for the lab calculations? All right, so next up, I want to talk to you about the calculations for the post-lab discussion questions. So first off, where they say this part B, blah, 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 we've already done this. That was number 6, so don't worry about this right here. You have already done it in number 6. All right. So next up, discussion. So I'm going to let you skip A and B because they're kind of confusingly written, and we're going to start with C. So if you have your lab out right now, go ahead and skip A and B for number 4, and we are going to start with C. All right, so here it says the formula of nitrogen oxide is NO, and of nitrogen dioxide is NO2. They want you to write a balanced equation for the reaction, and they say of nitrogen oxide with oxygen. What they don't really tell you here is you are going from nitrogen oxide, you're adding in your O2, and your product, which is kind of hidden down here, is NO2. So you still need to balance, but I wanted to help you out writing that equation just because the product's kind of hidden in there. Okay, so now you have 3 questions, and the most common mistake that I find on this is that students only calculate one answer, and we're actually looking for 2 answers for each one of these. One is for oxygen, one is for NO2. So first off, it says how many moles of oxygen are consumed and how many moles of NO2 are produced. You need to start here. So start with, I have so many highlights in here. So start with that 1 mole of NO. So for part 1, the most common mistake that I see is people just give me the coefficients in the balanced equation. So you need to actually calculate it out starting with that 1 mole of NO and then do your mole to mole conversion. And again, you're going to do it twice. First time, or doesn't really matter the order, but let's just say the first time will be O2 and the second time will be NO. But make sure you do it twice. And again, it's a mole to mole conversion. So questions on part 1 here? All right, so next up is part 2, and it says how many liters of each, in parentheses, state conditions. When they say state conditions, they really mean STP, 0 degrees Celsius and 1 atm. And what you know, the special trick you learned about STP is this right here. 22.4 liters are 1 mole, or I should say 1 mole is 22.4 liters at STP. So my recommendation is to use that conversion. You're going to find out the moles in part 1 and then just use this conversion here to convert in between moles and liters. But again, you're going to do it twice, once for oxygen and once for NO2. So any questions on anything there? All right, so now let's talk about part 3. 3 says how many grams of each. So here you're going back to part 1 again. You know how many moles, and you're just using your molar mass to go from moles to grams. Where people get stuck on number 3 a lot is they will try to use number 2 to go into number 3, but you're actually going all the way back to number 1, because number 1 gave you the moles, and then you just want to do a mole to gram conversion using that molar mass. Again, you're going to do it for both oxygen and for NO2. So for all 3 of these, you need 2 answers, one for oxygen, one for NO2. So any questions on this part C here? All right, so again, I've written out your equation, but you do need to balance it. If you don't balance that equation, you won't get the correct answers here. Oops. Let's get some of these highlights out of your way so it doesn't look too overwhelmingly super Crayola colored. All right, next up in part D, it says calculate the mass of 4.55 liters of HCl gas at STP. So here you want to use that conversion again. So this is a gas, and if it's at STP, we're going to assume that 22.4 liters to 1 mole conversion works. So I would recommend first go from liters into moles, and that's why it says find the moles first, and then just do your moles to grams conversion. So any questions on part D? All right, so let's move on to part E. So part E says find the molecular mass, which is grams per mole, of a gas having a density. Oh, so it looks like hopefully it got changed in your book, but it looks like there's kind of a weird typo here. Find the molecular mass of a gas having a density of a gas. Oh, it looks like the words are repeated here. Of a gas. There we go. Having a density of 0.00481 grams per milliliter. I hope that got changed in the new version of the lab manual, but I have a feeling it probably didn't. That's okay. So here's your density right here. And we are at STP, which you know means 22.4 liters per mole. Here is my hint to you, and that is if you assume 1 milliliter, then you can convert 1 milliliter into liters and then convert liters into moles. That will give you the moles that you need for the bottom. And this density is already written in grams per milliliter. So if you have the milliliters, that becomes your grams. So again, if you're in 1 milliliter, which is what I recommend, your grams literally are the density. So any questions on anything there? Let's see. 1.55 liters per mole, 4.55 liters per mole. So Jervin, are you asking about part D? Yes, okay. So let me just finish up with E. Any questions on E? Okay. So get this out of your way. All right, so for part D, these are your liters, but in terms of your liters per mole, it's this right here. So what you're going to do is you're going to start off with the liters, and then you're going to use this conversion down here to do liters per mole, and then you'll go into grams. But this right here is 1 mole for every 22.4 liters, and you'll plug that one in there. Does that answer the question, sort of? So that's just this, this relationship that we've been talking about. Anytime you're at STP, it's always 22.4 liters per mole. And it's something that we used above here as well. You're going to use it in part C as well. 22.4 liters per mole. And you actually are using it even in the, you're using it in your percent error as well, because that's the accepted value, so you're comparing your answer to that one. Does that answer the question? Oh, STP, no problem. So STP, let's just grab a fresh page. All right, so STP is our standard temperature and pressure. So in class we said 0 degrees Celsius and 1 ATM, but for this lab we're going to be using it in Kelvin, so 273.15 Kelvin, and you'll use 760 torr. So other questions so far? Okay, excellent. And did that answer your question about part D? All right, I guess I'm going to take no, yes, okay, perfect. Oops. All right, good enough. There we go. All right, then let's see, we talked about E, so F is the tricky one. So F first says write the balanced equation for the reaction that occurred in this lab. So remember, I actually gave that to you. I didn't balance it for you, but I gave it to you way up here. So they're asking for this balanced equation. All right, and they're going to give you two different situations. So be aware that these are different. So one is assuming that you have pure KClO3. So if you have pure KClO3 and you know your mass, and it's given right here, 2.550 grams, then what we want you to do is use stoichiometry to find everything. So it says there will be blank moles of O2. So you're going to assume that this number of grams is all KClO3. So here you're using the KClO3 to find the O2. So again, this is going to be a conversion, just grams of KClO3 to moles of O2. So it's almost like a grams to grams conversion, but you're going to pause and write down the number of moles, and then you'll finish out that gram to gram conversion, and then you're going to write the grams here. So this is a moles to grams. So again, it's overall a grams to grams conversion, just like we've done. It's just they want you to pause and write the number of moles of O2, and then you get to write down the grams of O2. So any questions about this first part where you're writing down the moles of O2 and the grams of O2, just doing a conversion, standard stoichiometry conversion? And this is part 1 of letter F. All right, so next up, they say that it occupies blank number of milliliters at STP. So I've numbered this one, 1 right here, and it goes to 1 right over here. So once you know your moles, you can use this conversion that we're using all over the place in this lab, and that is 22.4 liters equals 1 mole. So again, you're going to take the moles that you found, and you're going to convert them first to liters and then to milliliters using that molar volume. 22.4 liters equals 1 mole. So any questions about the one that I've numbered 1 here? All right, so next up, oh, yeah.
For the first blank, does that say SKClO3?
Let's see. So are you talking about in the typed part or where I'm writing?
Yeah, I can't really read that. Where it says there will be blank moles of O2, above that.
Oh, okay. That is my very poor handwriting. Let me zoom in here. So this little guy is grams of KClO3 goes to moles of O2.
Okay, cool. Thank you.
No problem. And yeah, if you guys can't read my handwriting, please do let me know. All right. So any other questions or any questions on that one that I labeled number 1? All right, so let's move on to the one that I've labeled number 2, and I've been resisting using hot pink. I know so many people don't like that. We will choose this paisley unusual color. All right, so number 2 is next. Okay. All right, so number 2, you are going to use your combined gas law, PV over T equals PV over T, to find the new volume. So on the right-hand side, you're using the given conditions. The given conditions are these right over here. And you're trying to find the new volume. So you are going to plug in pressure at STP. and you're going to plug in temperature at STP. Remember, the units need to match. So we gave you pressure and torr right here. And so you need to keep that pressure and torr at 760. So again, on the right-hand side are the given conditions. These are the ones that are coming from the problem. These ones right here. Sorry if I'm going a little crazy with the highlights. And on the left-hand side, these are conditions at STP. So you're solving for the volume. So you're going to plug in pressure at STP and temperature at STP. So any questions on number 2? All right. All right, and finally, we're still on F, and this is part 2 of F. Now we're saying that you have a mixture of KClO3. So we're using the same number of grams of sample, but now we're saying your sample was not pure. All right, so here it says, assume that the sample was a mixture, and this is what it yielded. 182 milliliters of oxygen gas, 29 degrees Celsius, and 732 torr. So this is what you got for your data. Now we want you to calculate the mass of KClO3. Here we cannot do a gram to gram conversion because you did not start with all KClO3. So instead, you're going to use PV equals nRT to find the moles of oxygen. So you know your pressure, right up here, 732 torr. You're going to convert that into ATM. You know your temperature, 29 degrees Celsius. And because we're now back to gases, you're going to convert that into Kelvin. And you know your volume, 182 milliliters, which you'll convert into liters. And you know your R value, so you're just solving out for the number of moles. So once you find your moles of O2, now you can use your balanced chemical equation to go from the moles of O2 into grams of KClO3. And once you do that, you're going to place that answer on the top, and the bottom will be the original sample, which was way, way, way up here. The one that I've colored in 3 different colors now, 2.550 grams. That was your original sample. And that goes all the way down here in the denominator. All right, so I know that part 2 is a little on the confusing side, but any questions there? All right, and if you're wondering, oh my God, these are so much fun, do we get to do another one? There is one more part, and that is part G. So here we have nitrogen collected over water at 26 degrees Celsius and 755 torr. The volume collected is right over here, 35.9 liters. What volume would it occupy dry at STP? All right. So here you're using the calculation in 6 from the lab. So same calculation that you did for the lab, and now you're using it here. So we're trying to find V2, P2 right here, and T2 right here. Those are your STP values. So remember, if you're in torr, that's going to be 760 torr for the pressure, and for Kelvin, of course, 273.15. And now over here, you want to use the data given in this problem. All right, so your volume given was this one right here. Your temperature given was this right here, but watch out for that torr here. Because we were told it was collected over water. So remember, anytime it's collected over water, this is P total. And this right here is the P of your gas. So remember, that is P total minus P of water. So remember, if you collect over water, you must subtract out the pressure of the water. So you're at 26 degrees Celsius. So you're going to go back to that same chart. And you're going to look up 26 degrees Celsius, and that is where you'll find your vapor pressure in torr. Let me make a note here. This is in torr. Okay. All right, so questions on anything here for Part G or anything else that we've talked about? All right, so that was the end of the discussion questions here. So this is not due until after spring break, but I encourage you to get it done as soon as you can. I will be here till 9:45. But do y'all have any questions on anything from the lab, anything from the lecture, anything about that upcoming exam? All right, so for those of you who are exiting now, I will see you later. I will get this Zoom fixed so it doesn't keep telling you that your host is already in another meeting. So by the time we get back together Monday after spring break, I will get that fixed, or I will have that fixed. Those of you who would like to stay, feel free. I'll be here till 9:45. And again, you can always check out and then come back because I'll hang out here and wait for you till 9:45. And I will see the rest of you after spring break. Have a wonderful spring break. Bye, everyone. Bye, guys. Yes, take care. Stay safe. Enjoy your time off.